folks! Today we will make the most advanced deep learning application in the history of this channel. We will use Stable Diffusion to generate images from a piece of text. We will then enlarge them using super sampling techniques, and we will wrap it in a beautiful GUI application that runs from a Docker container. And the best part is, we will delegate all the generative tasks to our GPU, making our app incomparably faster. It's the most professional and coolest workflow that I've ever simplified, and the results will absolutely blow your mind. So without any further ado, let's roll. So let's begin by installing Docker Desktop. For this, we will navigate to docker.com, and from the Products menu, we will select Docker Desktop. Now, if you are not familiar with Docker, I have an amazing tutorial that covers it in detail. But the general idea is we want to isolate our application from the rest of the computer. We want to make sure it runs consistently in different conditions, environments, and even operating systems. And that way, users don't need to install a bunch of libraries trying to recreate the exact same environment that us developers have. They can just run a Docker container with our software and all its dependencies already installed. Now, once Docker Desktop is on our system, we will go ahead and make sure that the engine is running given this green bar at the bottom. Additionally, if you are planning to use a WSL terminal like myself, we will navigate to the settings and we will make sure we enable it by checking this lovely box right over here. Once we do so, we can then safely navigate to our Windows subsystem for Linux, and we will use it to clone some starter files from GitHub, where I created a very nice interface that doesn't have any functionality. There are buttons, but nothing happens when you click them, so we are basically building this project almost from scratch. For this, we will copy the HTTPS address of my repository, and we will paste it inside our terminal following a git clone command. Then we will navigate to the brand new directory we now have on our Linux drive with cd, followed by Stable Diffusion GUI app. In addition, we will navigate to the starter files folder, which from now on I'll refer to as the root directory of our project. Now, to make it work, we will need to set up a Docker container, and the fastest way to do so is by using Docker Init. Now, unlike previous tutorials where we manually typed a bunch of code into our Docker file, we are now automating this process. So Docker Init will ask some questions, and based on our answers, it will generate all the files that our container needs. In our case, it already detected that the platform we use is Python, so let's just press Enter. And while Python 3.11.5 is the officially recommended version that you should specify on your end, I will go for Python 3.10 instead. I do it on purpose. You will see towards the end of the video why. Then the port of our choice would be 8000, and the running command we are planning to use is python 3 app.py. And beautiful. Docker successfully initialized all the important files. There you go. And we can now run our application by copying this lovely command of docker compose up --build. Once our container is ready, we will open our browser and navigate to localhost at the port of 8000. And boom, here's our beautiful starter application that doesn't really do much. So let's investigate it a bit. And the first thing we'll do here is enter some kind of prompt. Let's say, Canadian bear eating fish in the river. Now, once we hit the generate button, our app should produce 3 different images based on our prompt. But at this point, the only thing it does is collect the user input and print it to the console. You can, of course, view it inside the terminal, or alternatively, if we navigate to Docker Desktop, then we navigate to the containers bar, choosing our starter files server, we can find our user input in the logs as well. So if the input is already being collected, then we just need to convert it from a piece of text into an actual image. For this, we will need a generative AI model, which in our case is Stable Diffusion in the version of 1-4. But how exactly can we use it? Well, approach number one is what we've done in previous tutorials, where we simply copied this type of code and we were pretty much good to go. But the only problem with this approach is that it takes way too long to load and operate. So approach number two is downloading this entire model into our local computer. And it does require some disk space. Specifically, I am talking about 40 gigabytes of it, which I know sounds like a lot, but very often when you're dealing with these type of models, you'll be looking at hundreds of gigabytes instead. So as far as I'm concerned, it's just a baby. Now let's go ahead and copy the URL of this model card, and you can check out the description for all the links. We will then navigate to our terminal. We will shut down our container with Ctrl-C, and we will download Stable Diffusion with git clone followed by the URL of our model card. And as you may guess, it will take quite some time to download. And if your download only took a few seconds, it obviously means that something is wrong. I mean, these numbers, they're not really adding up to 40 gigabytes. So let's fix it. We will need a package called gitlfs, which we will download with sudo apt-get install git-lfs, as in git large file storage. You will hit enter. Then we will call gitlfs install. Then we'll of course get rid of this incomplete directory we just downloaded. Let's delete it. And now we can go ahead and clone our model once again, this time properly. So git clone followed by the Hugging Face repository. Great. Now once our model is done downloading and we can find it inside our root directory, we can then go ahead and update our requirements file, adding a library named Diffusers, which uses the transformers architecture as well as the Torch deep learning framework, also known as PyTorch. Lastly, we will add the accelerate module, which will help us with loading our model on CPU in a memory efficient way. Now let's save it and we can finally start coding. So inside our app.py file from Diffusers, we will import the Stable Diffusion pipeline in upper camel case. Then right below our secret key, we will create a new variable named pipeline, which we will assign to the Stable Diffusion pipeline class, calling the from_pretrained method on it. And into this method, we will pass the path to our model, which in our case is /, which represents the root directory, followed by the name of the model repository, which is cloned. So let's just copy it from our file system. And there you go. This is where our model now lives. Now, this pipeline produces very basic images. They are nice, but they're not as realistic as we'd like them to be. So let's fix it by typing pipeline and calling the enable_FreeU method on it. Now, this method allows us to customize 4 different quality control parameters. And in my case, I'll just use what's recommended for the Stable Diffusion 1.4 model. I'll copy them directly from the FreeU repository. And if you're curious to see some examples, this is the type of quality improvement that you'll get. Awesome. So let's go ahead and paste these parameters inside our enable FreeU method, replacing every colon with an equals symbol. Now, to produce our image, we will find the app route where we collect our user input and print it to the to the console. So right underneath our print statement, we will type pipeline, to which we will pass our user input. So let's just copy it from the print statement right above, and let's pass it right over here. Then we can assign this expression to image. And at this stage, let's just see how this data structure looks like. We'll have a better idea of what we're dealing with here. Let's save our file. Let's go back to our terminal and let's call docker compose up -- build once again. We will then navigate to our browser, then to our app, and we will remove the prompt root from the URL. Then we will enter the same input from before, and after quite some time, our image was generated, so we can navigate to our terminal where we can find our output. Now, this output has two different arguments. The first one is images, and it stores a list with a single image item. And that's exactly what we're looking for. The other argument stores whether our image is safe for view or not. And in our case, it is perfectly safe because you want it to be false. Great, so now we can just go back to our code. We can focus on the images attribute of our pipeline, and since it stores a list, we will focus on the first and only item in this list. Then instead of printing this image, we will go ahead and save it with image.save, and we will call it, at least at first, output.png. Now, currently, if we make changes to our Python file, our container doesn't automatically detect them. We will need to shut it down and rebuild it time and time again, which is probably not ideal. So let's fix it. The first thing we need to make sure is that our debug mode is set to true, which is of course true in our case. If so, we will navigate to our Docker compose file where we will add a new attribute of volumes. And we will use this attribute to mount the local root directory / to the container directory of /app. But wait, how come it is /app? Where exactly can we find this detail? Well, let's save this file and let's navigate to our Docker file, where we can see that the working directory of our container is indeed /app. And that's the only reason why we chose it. If it says something else on your end, that's what you should write instead. Now, if we're already here, let's have a look at another detail. So by default, Docker Init creates a special kind of user called app user. And this user has very limited access. They can use the app, but they cannot make any changes, such as saving images, which is a problem in our case. So let's go ahead and remove this unprivileged app user, replacing it with the system administrator, also known as root. Otherwise, you will get a permissions error that looks like that. And great, now we can save our file, we can navigate back to our terminal, we can shut down our container for the very last time with Ctrl+C. We will then rebuild it with all the changes we just made. We will enter our original prompt. We will then navigate to our root directory where we will find our lovely Canadian bear. Yay! Now let's apply the same logic on 3 different images, storing them in the appropriate location of static images, and there you go. We can find our logo and our placeholder ? Image here. So back in our code, inside app.py, right above our image variable, we will go ahead and create a for loop with for I in range 3. Then we will indent our image pipeline as well as the image saving command, and instead of output.png, we will navigate to static/images, and we will give unique names to each of our images. We will do so with demo_image, to which we will concatenate the string instance of I, which is our iteration variable from above. It is either 0, 1, or 2, which will be the unique portion of the image names. Then we will wrap it up with the file extension of .png. And if we're already here, we may as well display those images on the page. So let's just copy the names of these images and let's paste it right underneath inside the prompt images list comprehension that we are passing to our render template return statement. So instead of displaying our placeholder images 3 times in a row, we'll just go ahead and display the actual demo images. And since this list comprehension also uses the iteration variable of I in the range of 3, everything should work like a charm. So let's save it, let's go back to our browser, and let's give our Canadian bear another try. And wow, look at these beautiful, beautiful bears. It's pretty impressive, right? But the only problem is it took way too much time to produce these 3 images. And our CPU sounded a bit like a jet fighter in the process. So how exactly do we solve it? Well, why don't we use our GPU instead? Now, the next trick will only work if you have a CUDA-compatible NVIDIA-based graphics card. So if you can find it somewhere here on the list, then great. You can follow along and you can continue with the next steps. Otherwise, please skip to the super sampling part and I will see you in about a minute. Now, to access our GPU from Docker, you will need an NVIDIA driver, which I assume you already have because it's very rare if you don't. Additionally, we will need a container toolkit, which we can install using the following guide. And we will first copy the configuration command. We will then paste it inside our terminal, shutting down our container, of course. And once it is shut down, we can now paste it. Then we will go ahead and update our package repository, as in apt-get. And now we can finally install the container toolkit. We will then go ahead and scroll down and we will configure the container runtime. Lastly, it is recommended to restart Docker. So let's just do it. We will copy this sudo system control restart command. We will paste it back. And if you cannot do it from your terminal, just like in my case, we can just do it from Docker Desktop. Let's just hit the quit Docker Desktop button. We will confirm we would like to quit, and we will open it once again. Yay! So now we've set up our GPU, but we also need to notify Docker. To do so, we will navigate to another installation guide, this time the Docker GPU support guide. We will scroll down, and we will copy the Docker compose code right from deploy down to the very end. Then we will, of course, paste it inside our compose file right underneath volumes. And please make sure that the deploy attribute is at the same indentation level as the volumes attribute. Otherwise, you will get an error. Great, so we're officially good to go. How do we know? Well, let's save this file. Let's go back to app.py. And at the very, very top, we will import PyTorch. And we will print whether torch.cuda.is_available. Let's save this file. Let's navigate back to our terminal. And boom, CUDA is available indeed, given this lovely true statement at the very top, right above loading our pipeline components. Now, if it is false on your end, please leave me a detailed comment below so I can help you with troubleshooting. And the emphasis is on the detailed. Now, to delegate our tasks to the GPU, we will first turn our Stable Diffusion pipeline into a multi-line command, just so it is easier to look at. We will then call the to method on it, and we will send it to a device named CUDA. And now, if we save our file, if we navigate back to our app, our images are now ready within seconds and not minutes. Yay! And perfect, we are almost done. We just need to find a way of enlarging these images because right now they're pretty small. For this, we will need another deep learning model called EDSR, as in Enhanced Deep Super Resolution Neural Network. So from their GitHub repository, we will navigate to Models. We will then choose how much we'd like to zoom in. In my case, I'll go for ×4, turning 512 pixels into 2048 of them. Then, with a right click on the raw button, we will copy the link address. Now, since we don't need the entire repository, we won't be using git clone this time, but a command called wget followed by the URL we just copied. Now, once the download is complete, we will then take care of the requirements, which in the case of our super sampling model would be OpenCV-Python, as well as OpenCV-contrib-Python. But that's not all. If we try to install OpenCV with these requirements only, then we will get the following error. To fix it, we will need to install some operating system requirements that cannot be just installed with pip, so specifying them here is not going to work. Instead, we will navigate to our Docker file, we will copy the following command from the description, and we will paste it right after we pip install our requirements file. Now, if we save everything, and we'll make sure I save the requirements as well, because I can't remember, We will then navigate to our terminal. We will rebuild our container with docker compose up again. And now we can finally navigate to app.py and import CV2, also known as OpenCV. Now, OpenCV is a computer vision library that we've used many times on the channel before, but never in the context of loading neural networks. So let's see how it works. Now, first, we will create a super sampling object with cv2.dnn_super res, as in deep neural network super resolution, followed by dot and an abbreviation of DNN super resolution implementation _create. We will then assign this expression to a variable named super res. Next, we will load our model into this object with super res.read model in camel case, and we will pass the name of our model as it appears in our file system, into this lovely method of ours. So let's just copy it and let's specify it in a string. Lastly, we will need to set this model with super res.set model, where the first argument is EDSR and the second argument would be the scaling factor of 4 because we are using the ×4 model. And great, our model is ready to go and we can take care of the image that it's supposed to enlarge. For this, we will search for the super sampling route, which is the third and last route of our application, right above if name equals main. And in this route, we will type cv2.im read, as in image read, to which we will pass one of our demo images. But wait a second. How do we know which of our demo images was selected? I mean, we have 3 of them, right? Well, judging by this print statement above, we see that we need a bit of investigating. So let's comment out this incomplete line of code. Let's save our file and let's navigate back to our app. So what happens if we click on the leftmost save button? Well, first of all, our demo images disappear and they're being replaced by the placeholder, which is something we'll need to fix. But second of all, if we navigate to our terminal, we can see a message that save button 0 was clicked. If we click on the center button, then we see that button number 1 was clicked instead, and same goes for the rightmost button that returns button number 2, which is a perfect match to the way we named our images. We have image 0, image 1, and image 2, which allows us to load each of our images one at a time. So back in our code, we will go ahead and uncomment our hashtag from earlier, and we will pass the following string into our image read command. We will start with /, followed by static, followed by images, followed by demo_image, to which we will concatenate the identification number of our images, which we'll just copy from the print statement. And just to be on the safe side, we will convert it into a string. Then we will wrap it up with a .png extension, saving this very long line of code as demo_image. And now that we have a loaded image, we can then pass it into our super sampling model. We will do this with super res.upsample, to which we will pass our demo image. Then we will assign this expression to XL_image, as in extra large image. Now, the only problem is the upsample method returns a NumPy array, which is a mathematical structure rather than an actual image. So let's quickly convert it into one by using the image class with a capital I from the pillow module and calling the fromArray method on it, passing our NumPy array of XL_image into it. Now, we can then assign this expression back to XL image, overriding the original value with the new one. And now that we're dealing with an actual image, we can save it with XL_image.save. And at first, we will call it XL_output.png. We just want to make sure it works. So let's save our file. And before we forget, let's go ahead and take care of our placeholder images. To do so, we'll just copy our list comprehension from the prompt route and we will paste it inside the super sample route. Easy peasy. Let's save everything. Let's go back to our browser and let's generate some bare images once again. We will then pick our favorite image, in my case, this guy over here. Let's save it. And back in our file system, specifically our starter files folder, we can find our extra large image. And it has the right size. I mean, it's clearly bigger than 512 pixels, but the only problem is our colors are way off. Now, the thing to remember with OpenCV is that instead of using the common RGB format, it uses the much less common BGR format. So our color channels are completely flipped. To fix it, we will close this image, we will navigate back to our code, and we will convert our image to the right format right before we pass it into our model. To do so, we will type cv2.cvt_color, where the first argument is our demo image, and the second argument is the type of conversion we'd like to perform. In our case, cv2.color, in all caps, _BGR to RGB. Now let's assign this expression back to demo image, overriding our blue bear with the right colors. So let's save it. And if we go back to our app and we try to save this image once again, we will go back to our file system where our bear image now has the right size and the right colors. Now, the only problem is we need to save a collection of images rather than overriding the same file time and time again. So instead of extra large output, we need to give our images unique names. One way to do so is by using date and time. So let's navigate to the top of our code, and from datetime, we will import datetime. Then, right below, we will assign datetime.today to a variable named image ID. And just to stay on the safe side, let's also convert it into a string. And at first, let's go ahead and print it with image ID, to which we will concatenate our variable image ID. Let's save it. Let's navigate to our terminal, where we can find our unique combination of digits, counting the seconds as well as the milliseconds. So it's very unlikely that one image will override the other. Now, the only thing I don't like here is all those punctuation symbols as well as spaces. So let's get rid of them. And one way to do so is by using a chain of replace methods, where at first we'll replace a colon with an empty string. And we will do the same to the dash symbol, as well as a space symbol, and lastly a dot. If we save our file, once again navigate to the terminal, our ID only stores a combination of digits. Still unique, but no punctuation detected. So let's use it as part of our image name. For this, we will copy these two lines of code. Actually, let's cut them. Let's paste them inside our super sampling route at the very top. And we don't really need the print statement, so let's just delete it. Now, one more thing we can do is we can store our extra large images in a special directory. So let's create it first. Let's navigate to static images, and we will create a new folder, and let's call it saved. Then, instead of extra large output, we will first navigate to our new saved directory, and we will call our images image underscore, to which we will concatenate our image ID, and we will finish this string with a .png extension. Now, if we save our file, we can then see our complete app in action. So let's navigate there. Let's create some more Canadian bears. Let's save one of our images in super resolution. Let's save another one. And if we check our file system, we can see that our images are saved in a special directory under unique names. Yay! Now, to be fair, we can make the super sampling process a bit faster by connecting OpenCV to CUDA, but it's quite the process. So if you'd like to see how, please leave me a comment below. Now, before we can share our app, we need to take care of licensing. And the idea is, because we are using models that somebody else made, we also need to follow their rules. And in the case of our app, we have 3 different licenses, where the first one is the EDSR license, which you can find on GitHub. So let's click on the license, and let's copy the raw link just like earlier. We will then paste it in our terminal following a wget command. Then we will go ahead and rename our new license file, and we will call it EDSR license, just for extra clarity. And we will do the same for our Stable Diffusion license, clicking on this license tab on Hugging Face, expanding it by clicking on Read More, and then clicking on this Files button. And from this repository, we can go ahead and expand the license.txt file, copying this beautiful URL from up there, and getting it. Lastly, we will navigate to the FreeU repository, which also requires a license. And let's get it as well. And just like before, we will rename it to FreeU license. Beautiful. Additionally, we will get rid of both our output images that we were testing with, and same goes for our 3 demo images, because they'll be automatically generated by the app. So let's delete them. And lastly, we will delete our saved image collection, but make sure you keep the saved directory itself, because our app will not run without it. So it's very, very important. Now, once we made a few changes to our files, let's go ahead and rebuild our container with Docker compose up-build for the very last time. Now, once our image was built and updated, we can then publish our app on DockerHub. For this, we will go ahead and create a new repository, which in my case, I will call Diffuse Me. We will also fill in some basic information. I'll just do it off camera. And once we have a remote repository name, we will navigate to our terminal and find out the local name of our image. We will do so with Docker images. And in my case, the name is starterfiles-server. Now, we need this name to be a perfect match to our remote repository name. So let's go ahead and rename it using Docker image tag, followed by the local repository name. We'll just copy it. And with a colon, we will indicate the local repository tag, which in my case is latest. And then we will specify the remote name, in my case, mariasha/diffuseme. Lastly, we will give it a tag of 1.0 because it is the first version of my image. Now let's go ahead and hit enter. Let's type Docker images once again with no typos. And now we see a new instance of our image that matches the name of our remote repository. And in this case, we can just type Docker push followed by the remote repository name and the tag of 1.0. Boom. Now, if your access to DockerHub is denied, you'll just need to log in with Docker log in, specifying your username, Maria Shah, as well as your password. And once your login was successful, you can then go ahead and call your push command once again. And this might take you a bit of time. Now, once our image was pushed, we will navigate to DockerHub, we will refresh the page, and our app is officially public. But what happens if somebody else wants to use it? Let's test it. For this, we will get rid of our local image instances by navigating to Docker Desktop and then to this troubleshoot lovely section, where we will purge our WSL2 data. And once our purge was completed, we'll then go ahead and get back to our terminal and let's test our Docker images once again, where we get nothing in return, which means that we get the same starting point as our users. Next, we will go ahead and Docker pull our remote repository, Maria Shah, diffuseme in the tag of 1.0. To make sure this image is safe to use and it doesn't have any vulnerabilities, we will use a static analysis tool called Docker Scout. We get it automatically through Docker Desktop and we can access it with Docker Scout Quick View, followed by the name of the image and the tag of 1.0. And once our image was done scanning, we can see the total number of high, medium, and low vulnerabilities, where in my case, the vast majority of them have to do with the version of Python I chose. Now, if you'd like to see some detailed information, I recommend copying this docker scout cvas command, but on my end, I only care about the recommendations. So let's copy this one instead. Let's paste it in our terminal and let's hit enter. And as you may guess, my recommendation is to change the base image either to Python 3.12 Slim, either to Python 3.11 Slim, or to an Alpine version. Now, on my end, I'm not too worried about it, but if you are more picky and if you'd like to fix it, please navigate to your Docker file, scroll up until you find your base image commands, and change 3.10 to 12 as well as Slim to Alpine. And boom, now Docker Scout will be extra happy and your app will be more secure than before. Now, once we've scanned our image and found that it's safe, we can finally run our application. To do so, we will create a new directory that has nothing inside it with mkdir, followed by the name of test. We will of course navigate there with cd test, and we can finally run our app with docker run, setting the GPU's flag to all. Then we will set the ports flag to expose the local port of 8000 to the container's port of 8000 as well. We will also use the volumes tag that sets the current local directory of // to receive information from the container's directory of /app, /static, /images, /saved. And that way, we are only storing our high-definition images on our local file system. Everything else will remain inside the container. We don't need our Docker files, our Python files, or our 40 gigabytes of Stable Diffusion tools. No thank you. We only care about the high-definition images. Okay? Now lastly, we'll specify the name of our image, which in my case is Maria Shah /diffuse me in the tag of 1.0. Let's run it. Let's fix my typo because GPUs requires 2 dashes and not 1. And this time, let's go for something a bit less realistic. Let's go for a unicorn cat on the beach. A high definition photo at dusk. Oh wow, look at these beautiful kitties. So let's go ahead and save one of them on our system. Let's navigate to our new test directory where we can find our lovely unicorn kitty image in high definition, and yay, everything worked. It looks amazing. Good job. And thank you so much for watching. If you found this video helpful, please share it with the world and don't forget to leave it a huge thumbs up and all kinds of comments. If you'd like to see more videos of this kind, you can always subscribe to my channel and turn on the notification bell. I'll see you very soon in some more amazing videos, and in the meanwhile, bye-bye!